What would happen if Betelgeuse suddenly replaced the Sun at the center of our solar system? The first answer is more extreme than simply saying Earth would become hotter. Earth would no longer be a planet orbiting outside its star, it would be buried inside one. Betelgeuse is a red supergiant located somewhere between about 550 and 700 light-years from Earth. From that distance, it is one of the most recognizable stars in the night sky. Its reddish color, immense size, and irregular changes in brightness have made it a favorite subject for astronomers. But distance hides the true scale of the star. Estimates of Betelgeuse's mass place it at roughly 14 to 20 times the mass of the Sun. Its diameter may be between 640 and 10 times wider than the Sun's diameter. Even the lower end of that range is difficult to imagine, because the Sun is already more than 100 times wider than Earth. Expand the Sun hundreds of times, and the familiar architecture of the solar system begins to disappear. Mercury would be lost first. Venus would be swallowed next. Earth would lie inside the star's outer atmosphere, and Mars could also be engulfed, depending on which estimate of Betelgeuse's size is closest. The planet would not be safely circling a larger sun. It would be moving through the thin, turbulent outer layers of a red supergiant. Earth would be destroyed almost at once. Betelgeuse's visible surface is cooler than the Sun's, with an estimated temperature of around 300 degrees Celsius. That number may sound modest compared with the surface temperature of the Sun, but it is still hot enough to vaporize oceans, strip away the atmosphere, and reduce exposed rock, soil, and living tissue to gas. The oceans would not gradually boil over many years. They would be transformed by an environment thousands of degrees hotter than anything Earth has ever experienced. The atmosphere would expand, escape, and mix with the star's outer layers. The surface would be heated beyond recognition, while the planet's material was dispersed into the surrounding stellar gas. No shelter on the surface could survive. No atmosphere could block the heat. No evolutionary adaptation could occur because there would be no time for one. Replacing the Sun with Betelgeuse would mean replacing Earth's environment with the atmosphere of a dying massive star. The inner solar system would vanish before Betelgeuse reached its final explosion. Jupiter would stand near the outer edge of the star's enormous reach, and even if some of its bulk remained outside the visible surface, its environment would be radically altered. Its hydrogen and helium atmosphere would be heated by the star's radiation and powerful stellar wind. The moons would face an even more dramatic transformation. Europa's ice would melt. Ganymede and Callisto would be exposed to energy they have never received from the distant Sun. Other icy bodies would begin losing the conditions that kept them frozen for billions of years. The system's center would no longer resemble a planetary neighborhood. It would be a giant, unstable stellar atmosphere extending through the region where the inner planets once moved. Yet the same star that destroyed Earth would send warmth far beyond the orbit of Neptune. Betelgeuse may be up to 100 times more luminous than the Sun. Its surface is relatively cool for a star, but its enormous area radiates an extraordinary amount of energy. A body does not need to be close to Betelgeuse to receive significant heat. A temporary zone where liquid water might exist could stretch to approximately 316 astronomical units. An astronomical unit is the average distance between Earth and the Sun. Neptune orbits at about 30 astronomical units. The Kuiper belt begins beyond Neptune, while distant objects such as Pluto, Triton, and Sedna occupy even more remote regions. A habitable zone reaching 316 astronomical units would extend far beyond the planets most people associate with the solar system. Pluto could receive enough energy to alter its surface. Nitrogen and methane ices might evaporate or move through new cycles. Triton could develop a much more active atmosphere. Sedna and other distant objects could be warmed after spending most of their existence in extreme cold. Their surfaces might soften. Frozen materials could migrate across the terrain. Thin atmospheres could expand. Compounds preserved since the early history of the solar system could become chemically active again. For a short time, the outer system could appear to awaken, but warmth would not guarantee life. It would only create a temporary opportunity, and Betelgeuse would not remain stable long enough for that opportunity to mature. The star is not a young sun beginning a calm, multi-billion-year life. It is a massive star near the end of its evolution. Its new habitable zone might exist for thousands of years, or perhaps less, depending on the exact stage of its interior. That is not enough time for complex life to evolve on a frozen world from scratch. The solar system would gain heat, but it would not gain a future. To understand what comes next, we have to look beneath Betelgeuse's swollen outer surface. For most of its life, a star like the Sun converts hydrogen into helium in its core. That process releases energy, and the outward pressure from that energy helps resist the inward pull of gravity. Betelgeuse has already consumed the hydrogen that once powered its central furnace. It has moved on to heavier elements. Helium has been involved in later stages of fusion, and carbon and other elements may also participate as the core evolves. Each stage produces new material and lasts for less time than the one before it. Eventually, the core begins accumulating iron. Iron marks a critical boundary in stellar physics. Fusion involving lighter elements can release energy. Iron fusion does not provide the energy needed to support the star. Once the core becomes dominated by iron, the star loses the source of pressure that had been holding gravity at bay. The core collapses. That collapse happens with astonishing speed. The inner material falls inward, becoming denser and more compressed. The outer layers follow, rushing toward the center. Under extreme conditions, the collapsing core stiffens and rebounds, driving a shockwave outward through the star. The result is a supernova. Betelgeuse would not explode because it simply ran out of fuel in the ordinary sense. It would explode because its core could no longer produce the energy required to oppose its own gravity. The outer layers would be thrown into space with tremendous force. For a short period, the star could shine with the brightness of billions of suns. The material expelled by the blast would carry newly formed and newly distributed elements into the surrounding galaxy. Betelgeuse is already showing why its final stage is so difficult to predict. Its interior is filled with huge convection cells. Hot gas rises from deeper layers while cooler material sinks back down. On a star this large, those convective regions may be comparable to, or even larger than, the entire orbit of Earth. The surface is not a smooth, motionless sphere. It is a shifting landscape of rising gas, sinking gas, shock waves, and enormous bright patches. The star's visible surface can change as material moves through it, causing its light to fluctuate over periods of months and years. In 2019, Betelgeuse became dramatically dimmer than usual. Its brightness fell to roughly 1/3 of its normal level, leading to speculation that the star might be close to exploding. The event revealed something important, but it did not provide a precise countdown. Betelgeuse had expelled a large amount of plasma from its surface. As that material moved outward and cooled, some of it formed dust. The dust then passed between the star and Earth, blocking part of the light that would otherwise have reached us. The star had not necessarily lost most of its power. A cloud of its own material had simply moved into our line of sight. A sudden dimming can be a hidden detail of stellar instability rather than proof that the final explosion has begun. That episode demonstrated how complicated Betelgeuse can be. Its brightness may change because of internal convection, surface eruptions, or clouds of dust. Astronomers can identify signs that it is approaching the end of its life, but they cannot determine the exact moment when the core will collapse. The supernova could happen tomorrow. It could happen in 10 years. It could occur 10,000 years from now, or at some point during the next 100,000 years. From Earth, no exact schedule is possible. The consequences also depend almost entirely on distance. At its actual location, between roughly 550 and 700 light-years away, Betelgeuse could explode without physically destroying Earth. The event would be spectacular. The supernova could shine with a brightness comparable to the full moon, and it might remain visible even in daylight. A star could undergo one of the most violent events in the galaxy while leaving Earth physically intact, simply because it was far enough away. The first thing we would receive would be light. X-rays and gamma rays from the explosion would travel across space for centuries before arriving here. By then, their energy would be spread over an enormous area. At Betelgeuse's present distance, the radiation would probably be too weak to penetrate Earth's magnetic protection or cause major damage to the ozone layer. Material from the explosion would arrive much later, if it reached us at all. Expanding debris would need millions of years to cross the distance between the star and the solar system. So the initial experience would be a brilliant new object in the sky, not a shock wave moving through Earth's atmosphere. There is another strange consequence of that distance. Light travels at a finite speed, and Betelgeuse is hundreds of light years away. Every image we see is already old. If the star exploded at its physical location today, Earth would not see the flash until centuries from now. And if Betelgeuse appeared to explode tonight, the actual collapse could have happened hundreds of years in the past. The explosion would also be productive in a cosmic sense. Massive stars create and distribute elements that smaller stars cannot make in the same way. Carbon, iron, and many heavier elements would be scattered through space. Some of those atoms could eventually become part of new stars, planets, moons, and living organisms. The death of one massive star can provide the raw material for worlds that have not yet formed. But distance has a dangerous limit. Imagine placing Betelgeuse much closer, at a distance of about 160 light-years. Earth would still be far outside the star's physical reach, but the radiation from the supernova would be much stronger. The ozone layer could suffer substantial damage. With less ozone to absorb ultraviolet light, more of the sun's ultraviolet radiation would reach the ground. The effects would spread through living systems. Rates of mutation and skin cancer would rise. Plants and animals exposed at the surface would face a harsher environment, while auroras could appear over regions that rarely see them today. The result would be a worldwide biological crisis, but probably not an instant end to humanity. Some ecosystems could persist. Life beneath the ocean, underground, or under protective layers of rock would have better odds than organisms exposed directly to the sky. Human civilization could face severe disruption, but the atmosphere might remain capable of supporting pockets of life. At around 160 light-years, Betelgeuse would be a serious planetary emergency rather than an automatic sterilization event. Move it to about 50 light-years and the situation becomes far more severe. At that distance, the supernova could destroy much or all of Earth's ozone protection. Without that shield, ultraviolet radiation from the sun would reach the surface at lethal levels. The supernova would not need to scorch the ground directly. It could transform our own star into a continuing source of biological danger. The first casualties would likely include organisms that sit at the foundation of marine ecosystems. Phytoplankton are microscopic, but they support enormous food webs and contribute significantly to the balance of Earth's atmosphere. Coral reefs provide shelter and structure for countless marine species. Damage to these systems would spread through the oceans long before the consequences became obvious on every continent. When the base of a food web fails, the collapse travels upward through every species that depends on it. Fish populations would decline, predators would lose their prey, coastal communities would face the loss of fisheries and reef protection. On land, plants and animals would be affected by stronger ultraviolet radiation, disrupted food supplies, and atmospheric chemistry that no longer behaved as it had before. Gamma rays would add another layer of damage. The atmosphere could develop high concentrations of nitrogen oxides, producing a dense chemical haze. This would not merely reduce protection from ultraviolet light, it would alter the atmosphere itself and could contribute to changes in climate. Radiation, ozone loss, marine collapse, terrestrial disruption, and atmospheric smog would combine into a crisis on a planetary scale. At 50 light-years, the question would not be whether Betelgeuse looked bright in the night sky. The question would be how much of Earth's biosphere could survive the new radiation environment. That distance separates a spectacular astronomical event from a possible extinction-level disaster. Even so, the 50 light-year scenario would still be less extreme than putting Betelgeuse where the Sun is now. At its current distance, Betelgeuse is not on a direct path toward Earth. Its eventual supernova is a distant event. At 160 light-years, Earth could face atmospheric damage. At 50 light-years, the biosphere could be pushed toward collapse. At the Sun's location, Earth would be engulfed before the supernova began. The star's red color would not make it safe. Its cooler visible surface would still be thousands of degrees hot. Its brightness would not create a permanent refuge for the outer planets. It would only shift the region of intense heating outward for a brief interval before the star's core reached its final failure. The outer planets would experience a very different kind of transformation. Saturn would probably remain outside the visible surface of Betelgeuse, although the exact result would depend on the star's true radius. From Saturn's distance, the star would dominate the sky as a vast red-orange disk. It would appear incomparably larger than the Sun appears from Earth, and the side of Saturn facing the star would receive an extraordinary amount of energy. The rings would be among the first structures to change. They are made primarily of water ice, mixed with rock and dust. Under Betelgeuse's radiation, that ice would heat, vaporize, and disperse. The elegant rings known today could become a cloud of gas and fragments driven outward by heat and stellar wind. Titan would also be transformed. Its thick atmosphere is maintained by the cold conditions of the outer solar system. Methane can condense, evaporate, and rain across the surface because temperatures remain extremely low. Betelgeuse would disrupt that cycle. Methane and other volatile compounds would respond to the new energy, while Titan's atmosphere expanded and changed composition. The Moon would no longer be a frozen world under weak sunlight. It would become a heated body exposed to the radiation of a star nearing the end of its life. The orbital situation would be complicated by a second star. Betelgeuse has a companion known as Alpha Ori b. It is a young blue-white star with a mass of approximately 1.5 times the Sun's mass. The companion orbits Betelgeuse at a distance of roughly 4 astronomical units. If the pair replaced the Sun at the center of our system, Alpha Ori b would travel on an orbit in the vicinity of the present region of the outer planets, potentially near Saturn's orbit. This would introduce a second source of gravity into a system already being reshaped by Betelgeuse's enormous mass. Saturn's orbit could be disturbed. The companion might pass close enough to disrupt the planet or its moons. In a more extreme interaction, Alpha Ori b could be drawn into Betelgeuse, torn apart, or destroyed when the red supergiant eventually exploded. The new system would not be a simple solar system with a bigger central sun. It would be a temporary stellar complex containing a red supergiant, a nearby blue-white companion, altered planets, evaporating ice, and orbits that no longer followed their familiar paths. Estimates suggest that Alpha Ori b itself could be consumed within roughly 10,000 years. That may sound like a long time when measured against a human life, but it is extremely brief compared with the billions of years over which planetary systems normally develop. A stable system can become temporary when a massive star changes the balance at its center. The expanded habitable zone would face the same problem. Pluto and other distant objects could receive enough energy for liquid materials to exist under the right conditions. Triton, Sedna, and bodies scattered across the outer solar system could experience atmospheric expansion and surface changes. But a habitable zone is not automatically a home for life. A world needs stable temperatures, suitable chemistry, liquid solvents, and time. It needs geological and biological processes to continue without being interrupted by another catastrophe. Betelgeuse could provide warmth, but it could not provide stability. The star's final stages would arrive before complex life could take advantage of the new conditions. Deep in its core, iron would continue to accumulate. Fusion would fail to generate enough pressure. Gravity would pull the core inward. The outer layers would fall toward the center and then be thrown outward in the supernova. The temporary habitable zone would disappear. Any planets that remained in the enlarged system would be struck by a blast powerful enough to outshine the total energy the Sun is expected to release across its entire 10 billion-year lifetime. The outer planets might avoid being swallowed during Betelgeuse's swollen red supergiant phase, but that would not mean they had survived. The explosion would send radiation, shock waves, and rapidly expanding debris through the remaining system. Atmospheres would be stripped or chemically altered. Surfaces would be heated and battered. Moons that had briefly begun to thaw would be overwhelmed by the much greater violence of the stellar death. The planetary system would be converted into a cloud of gas, dust, and shattered material. That cloud would contain carbon, iron, and other elements, including heavy metals such as gold and platinum. Some of these elements would have formed during the star's life, while others would be created or scattered during the explosion. The planets would be gone, but their atoms would remain. Over millions or billions of years, the material could mix with surrounding interstellar gas. New stars might form from it. New planets could gather around those stars. Some future world could contain material that once belonged to Earth, Saturn's rings, Titan's atmosphere, or the outer moons. No observer would see the original solar system return, but its ingredients could be recycled into another generation of worlds. Replacing the Sun with Betelgeuse would not produce a larger, longer-lasting version of our planetary system. It would create a brief period of extreme heating, erase the inner planets, destabilize the outer system, and end with the star scattering everything into space. That contrast explains why the real Betelgeuse is both fascinating and comparatively safe. At hundreds of light-years away, its supernova would be a brilliant event visible from Earth. At about 160 light-years, it could damage the ozone layer and expose life to dangerous ultraviolet radiation. At approximately 50 light-years, it could threaten the atmospheric protection on which the biosphere depends. At the position of the Sun, it would engulf Earth before the final explosion even began. The danger would not come from the star's color, its flickering, or the fact that its surface is cooler than the Sun's. The danger would come from its scale, its luminosity, its unstable interior, and the removal of the distance that protects us. Betelgeuse is already unstable. Its enormous convection cells move through the star's outer layers. Its brightness rises and falls. Plasma eruptions can create expanding clouds of dust that temporarily conceal part of its surface. Those changes tell us that the star is in a late stage of stellar evolution, but they do not reveal the exact date of its death. It may explode tomorrow. It may explode 10 years from now. It may wait 10,000 years, or much longer. Astronomers can estimate the broad range of possibilities, but they cannot identify the precise moment when its iron core will collapse. When the explosion finally occurs, Earth will almost certainly still be hundreds of light-years away. We may see a new point of light become as bright as the full moon. We may see it during daylight. We may watch the death of a massive star while remaining safe from its immediate physical effects. The light will arrive first, carrying news from a collapse that happened long ago. The debris will move much more slowly, taking millions of years to cross the distance between the star and our planetary neighborhood. In that expanding material will be the ingredients of future construction: carbon, iron, gold, platinum, and many other elements. A star large enough to consume the inner solar system can also become one of the sources from which future planets are assembled. That is the strange balance in Betelgeuse's story. From far away, it is a spectacle. Closer to Earth, it becomes an atmospheric threat. At roughly 50 light-years, it could trigger a crisis capable of reshaping the biosphere. At the center of our system, it would destroy Earth before its final explosion. The actual star remains at a safe distance, burning through the last stages of its life. One day, its core will collapse. The night sky will change. A red giant that has been visible for generations will become a brilliant flash and then an expanding nebula. The star will be gone, but its material will continue traveling through the galaxy. Eventually, some of that material may become part of a new star, a new planet, or perhaps a new form of life. The end of Betelgeuse will erase its own system, but it may also help begin systems that have not yet been imagined. The universe does not treat destruction and creation as opposites. The same explosion that ends one world can supply the elements required to build another. And the most important factor in whether Betelgeuse is beautiful or catastrophic is not its temperature. It is the distance between us and the star. When Betelgeuse finally explodes, will Earth see the flash of a recent collapse, or will we be watching light from a star that died centuries before the event ever reached our sky?